Welcome to ePodasala lecture series in computer science. In this module, we are going to discuss about the NP-complete proof for certain important problems in computer science domain, such as traveling salesman problem, Vertex-cover, Clique problem. Then we are going to discuss about the sum of subsets problem. The learning objectives of this particular module is to understand the proof of NP complete problem. Last module we discussed some of the important aspects of NP completeness problem. We also discussed about the satisfiability problem, one of the most important in complexity theory. So, today module we are going to discuss more about the proof of NP complete problem. Then as an illustration we will discuss about traveling salesman problem, where we are going to discuss about how to prove that traveling salesman problem is an NP complete problem. Then we will also discuss about some of the other important problems in computer science domain, such as Clique problem, then Vertex-cover problem, and sum of subsets. Please recollect last module we introduced the concept of reductions. So, there are two types of reduction. One is Turing reduction, where we have seen that we have two problems A and B, where we have a problem for which solution is available. So, in Turing reduction we are just transforming the problem A to another problem which has got a solution. Then after getting the solution we are transforming the solution back to the original problem, that is called Turing reduction. The other reduction we discussed is CARP reduction, where we have seen that the input of the problem is called an instance. We have two problems A and B. So, U is the instance of problem A and V is the instance of problem B. Problem B is solvable. So, CARP reduction, what it actually does is it transforms the instance U to V in polynomial time, such that if U is yes, then V is also yes, and if U is false or no, then V is also no. This kind of reduction is what we are calling as the CARP reduction. One of the most remarkable discovery in computer science is CARP reduction, where we can take a problem and we can use that to reduce a problem A to another problem B. Last module we discussed how it is very helpful for us. Suppose if problem A is hard, and if a hard problem is reduced to a problem B, then B is also becoming a hard problem. On the other hand, if problem A is solvable in polynomial time, and if it can be reduced to another problem B in polynomial time, then B is also becoming a easy problem that can be solved in polynomial time. So, using this sort of reductions, we can give the proof of various problems. One of the other remarkable discovery in computer science is the Cook's Levin theorem. Last module we discussed how Stephen Cook and Levin independently formulated this theorem, that is the circuit SAT is NP complete. CARP, what he has done is he has taken some problems and he reduced the circuit SAT problem to those problems to prove the complexity of those problems. So, this is the starting point of the proof of any NP complete problem. So, recollect now that suppose if we are given a problem A we want to prove that it's a NP complete problem, then all we have to do is we have to take a well known NP complete problem and we have to reduce that problem to the given problem A. If that is the case, we can say that problem A is also NP complete. And the earlier modules we were also discussing about the characteristics of NP complete problems. You can recollect one of the important characteristic of NP complete problem is that we should have a certificate. So, what is a certificate? So, certificate is a case where we can say that the property of the algorithm holds good. So, that is called the certificate. Given the certificate, we can always verify whether the problem is right or not, that is called the verification algorithm. So, if we have a problem that has got a certificate and if it can be verified in a polynomial time, we can call those NP hard problems as NP complete problems. And also please recollect that NP complete problems are a set of problems where even if there is a solution for one problem, then the entire set will vanish. In other words, we can say that even if one problem is solved, then the entire set can be solved by the concept of reduction in polynomial time and there won't exist any such problem set. These sort of problems are what we are calling as the NP complete problems. So, to illustrate these concepts, we will take some couple of examples and then we will try to give you a proof. So, first we will take a problem called traveling salesman problem. You can know that traveling salesman is also known as traveling salesperson problem, TSP. In earlier modules we discussed this problem as part of dynamic programming, etc. So, we are just taking the same problem and you can recollect that traveling salesman is a NP complete problem because if the number of cities becomes larger, then finding the tour is a difficult one. So, tour is you have to start from one vertex, then you have to visit all other cities, then you have to come back. If you have such tour which is of least cost, then we can call that as the least cost tour and the solution of the traveling salesperson problem. And what we are going to do is we are going to take a very hard problem and then we are going to reduce that to traveling salesman problem, so that we can show that traveling salesman problem is NP complete. So, for that we are going to take the Hamiltonian cycle because Hamiltonian cycle is a NP complete problem. So, Hamiltonian cycle is a cycle where you start from a city, you visit all other cities only once and then we are coming back to the city where we have started. So, what we have to do now is we have to prove traveling salesman problem is NP complete. So, we take a well known NP complete problem, that is Hamiltonian. So, the first step is we have to reduce the Hamiltonian cycle problem to the traveling salesperson problem in a polynomial time. If we could able to reduce that in polynomial time, we can say that the first part of the proof is done. So, to do that we require a certificate. Do we have a certificate for finding whether a Hamiltonian cycle exists or not? Means yes, all we have to do is we can use a educated guess, and we can generate a sequence of cities, that is called a certificate, and given a certificate we can always verify whether it is right or not by means of a verification algorithm, where we have to check whether such a tour exists or not, where the criteria is that the tour starts from a city, then it visits all other cities, then we come back to the city where we have started. So, and we have whether the tour has got the length of k in polynomial time or not. This is called the verification algorithm. It is quite easy given a sequence to check whether it is possible or not. Therefore, the verification algorithm also exists. So, the first step is proving that traveling salesman problem is a NP hard, because we can say that it is tough, and it is NP complete because it has got a certificate as well as the verification algorithm. The second step is we have to reduce what you say the Hamiltonian cycle to traveling salesman problem in polynomial time. So, for that we have to show that reduction is indeed possible. So, what we are trying to do is we are trying to take the arbitrary g instance of the Hamiltonian cycle, and then we are trying to construct a graph g prime, and we are going to give the bound integer k such that the graph has got Hamiltonian cycle if and only if g prime as a tour of length k. So, in other words the traveling salesman will have a tour of length k if and only if the original graph has got the Hamiltonian cycle or not. So, in other words what we are trying to do is we are trying to construct g prime which is going to be a complete graph of all vertices v. So, all the original vertices of the original graph are retained, and E is such that if there is an edge in the original graph, then it is also have the edge in the what you say g prime, and we are going to assign the length like this. So, what we are going to do is we are going to assign the length of 1 if E belongs to what you say E, otherwise it is going to be n. So, this is going to be the second step. So, how many vertices will be there in G prime means fine, it is going to be n. So, that means the constructed graph G prime is going to have all the vertices of the original graph. So, the traveling salesperson involves a tour of all the cities. So, that means all the vertices should be present. So, all the path are assigned a length of 1. So, that means you can say that it is going to be k. So, that means if we assign k equal to 1, we can observe that such a tour is possible. In other words, if the graph G has got a Hamiltonian cycle, then G prime will have a tour of exactly length n. So, that means you can say that by assigning the weight of 1 to all the edge, we can say that it is of length k. So, that means we can come to a conclusion that this is indeed possible only if the Hamiltonian cycle is there. So, this is a kind of proof you can argue. So, in other words, you can break up the proof in 3 components. The first component is to prove that traveling salesman is indeed NP complete. Number 2 is we take a well known problem and then we are trying to perform reduction in polynomial time, and the third step is we are arguing that the problem is as difficult as the original, and if the problem can be solved there, then it can be solved here, and if the problem is not solvable there, then it is also not solvable here. By arguing that, we can say that both are what you say equivalent. So, this is the kind of proof you can give for traveling salesman problem. I hope you have understood. So, we will take a couple of more examples to illustrate this methodology. So, as a second illustration, I am taking a Clique problem. So, what we are going to do is we are going to prove that Clique problem is NP complete. So, how I am going to give you a proof for this? For this, I am going to take a satisfiability problem which we discussed in the earlier module, and then by reducing that sat to Clique, we can give you a proof that Clique problem is indeed NP complete. So, before we start, let me explain what is a Clique problem. So, we have a graph G equal to V comma E, where V is nothing but the set of vertices and E is nothing but the set of edges, and a positive integer k is given. The question is does G contain a clique of size k? So, clique k is a complete subgraph of graph G on k vertices. In other words, given a graph, you have to find the subset of vertices that are fully connected with itself. So, that we have a subgraph of k vertices to call that as the clique. We can take some of the examples of clique. You can say the triangle. Triangle is what you say a clique, where you can see that a node is connected to all other nodes. So, triangle will qualify as a clique. In other words, you can say that triangle is a clique of size 3. You take this example, this is a graph where you have vertices A, B, C, D, E and F. So, the Clique problem is can you say a subset which is going to be a complete subgraph, means you can say B, C, D, E is going to be a clique which is completely connected graph, where you can see that there is an edge between any node to any other node. You can also say that there is a clique exists between B, C and D and also C, D, E. So, this is also a clique of size 3, but in clique we have to find the maximum clique. So, that means we have to find the clique of the maximum k. So, in this problem you can say that the maximum clique size is 4, that involves the vertices B, C, D and E. So, this is the thing. Satisfiability problem, last module we discussed, you can say that this is nothing but a Boolean formula. So, the Boolean formula has got a literal something like x1 or x1 bar, and if we combine all the literals by means of R, we get a class. In other words, a class is a set of literals that are connected by R, and a formula is one which has got a form something like a set of classes that are what you say connected by AND. So, that means you have m classes. So, the question is for proof we are taking the satisfiability problem which is already proven to be NP complete as per Cook's Levin theorem, and by reducing this to Clique we are going to argue that Clique problem is indeed NP complete. Fine, you may find it very difficult to visualize how a problem having a formula can be reduced to a problem which is of graph. This is the real hurdle in giving proof for NP complete. So, that means we have to be creative enough to think about reduction, so that one problem can be reduced to any other problem. So, the reduction is done like this. So, that means what we are going to do is we are going to construct a graph using the formula. So, the formula has got what you say literals. So, literals you can recollect that involves both original as well as its negation, that is x1 and x1 bar. So, that means you can see that there are 2n literals are there. So, that means you can say that the graph will have vertices whose size is nothing but 2n, and the edges are connected like this where you have two classes xi and xj. So, what we are going to do is we are going to connect x1 to xj such that x1, xi and xj belongs to two different classes. And also you can see a condition here that the corresponding thing should not be a negation. In other words, I should not connect what you say x1 to x1 bar. So, in other words, if I say that two vertices are connected by an edge and these two things should not be contradicted to each other. In other words, it should not be something like x1 and x1 bar such that assigning true to x1 as well as x1 bar is prohibited. So, such a non-contradictory assignments are possible only if a literal is not connected to the negation of that particular literal. So, using this condition we can construct the graph. So, you can see that you have a formula like this. So, x, y bar and z, you can see that all the things forms one node, and x bar y forms another node, and you can see that x bar, y bar and z forms another node. So, now you can see that x is connected to all other literals in other classes like y, then z, then y bar and all. But you can see that x is not connected to x bar, and similarly x is not connected to this x bar. Similarly, y bar is not connected to what you say y. In other words, we are ensuring that the condition that if the edge connects two literals, they are not a negation of itself. By ensuring that, what we are getting is we are getting some sort of a graph like this. This is a reference source where you can find this particular problem. So, now what we are trying to do is we are trying to do this reduction, and then we are going to say that f is satisfiable if and only if G has got a clique of size m. So, that means we can say that the formula f is satisfiable where the formula is having class m is possible only if the G has got the clique of size m. So, this can be what you say argued like this. The a clique of m corresponds to assignment of true to m literals in m different classes. Please recollect, the formula is nothing but the AND of all the classes C1, C2, C3 etc. So, if that has to be true, then all the classes C1, C2, C3 etc. should have at least one true, then only the formula is what you say will be equal to 1. So, that means since m different classes are there, so at least m literals should be assigned to true. In other words, in the graph that corresponds to a clique of m, and also you can recollect that the edge is always between only the non-contradictory nodes. So, that means we are not connecting x to x bar. So, that means you can say that true can be assigned either to x 1 or it can be assigned to x 1 bar. So, having said that, now we can obviously make a claim that f is satisfiability is satisfiable if and only if there is a non-contradictory assignment of true to m literals. And since this m what you say assignments corresponds to m clique of the graph, we can say that this is possible if and only if G has got a clique of size m. So, this is the argument. We can say that fine, if the formula has to be true, then all the classes should be true. So, that means at least one literal should be assigned the value of true. So, in graph equivalently we can say that that is available as a node. In other words, that should have the connectivity. Therefore, this is possible only if m cliques are available in the graph. So, this is the proof of this particular problem. Okay. We can also extend this for vertex cover. So, in vertex cover what we are trying to do is we are given a graph G equal to V comma E, and we are given a positive integer k. So, in vertex cover all we have to do is we have to find the subset C of size k such that each edge is incident to at least one vertex in C. This is called the vertex cover problem. So, this is the example of a vertex cover. You can say that so is 1 and 2 is vertex cover means no, because you can say that 4, 5, 5, 6 and 3, 6 are not covered by the vertex cover. And what about this? Is it vertex cover means no, because you can say that 4 to 5 is not covered by that. And what about this? Is it vertex cover? Yes, it is vertex cover, but this is of size 6. So, this is also not optimal. So, in short, the vertex cover problem is a problem where given an undirected graph, we have to find the vertex cover with the minimum size. Fine. What we are going to do is we are going to prove that this problem is indeed NP complete. So, what we are going to do is we are going to take the SAT problem and then we are going to reduce that to what you say this sort of vertex cover problem. So, again you may wonder how a formula can be what you say reduced to a graph problem. So, these are certain formula. So, you can say that every variable xi we connect xi and xi bar. So, every class contains nj literal means then we are creating a clique of size nj, and then we connect all the nodes of the clique to the original what is a vertices, then we can say that this is of size k, this is a cover. So, you can take this particular example, you can say that this is the formula. So, you can see that by rule 1 we are connecting the literal to its negation. You see x bar is connected to x, x is connected to x bar, z is connected to z bar. Then we create clique. So, this contains a clique of size 3, this contains a clique of 2. Then we are connecting all the things by means of edges. This is called the connecting edge, and we can say that this is of what is a covered by what is a vertex cover k. Then you can argue this, you can say that f is satisfiable if and only if the constructed graph has got a vertex cover of size k. So, the argument is like this: if xi is assigned true, then we are going to add this as part of the cover, otherwise we are going to add xi bar to the vertex cover. So, that means if f is satisfiable, then we can say that it will have a vertex whose corresponding literal is assigned the value of true. So, that means the edge u comma v is covered. Therefore, you can say that all the n j minus 1 vertices will be add to the c j to the vertex cover. So, that clearly we can say that the vertex cover is going to be like this. We can also reverse also, that means f is satisfiable if and only if the constructed graph has got the vertex cover of size k. In other words, we can argue easily that one is possible, so that the other is also possible, and the other is not possible without the first case is possible, similar to the arguments we made in earlier cases. In short, we can come to a conclusion that by arguing like this, we can give the NP complete proof of all these problems. Summary, we can give the NP complete proof by reducing a well known NP complete problem to the given problem. We have given a proof that TSP is a NP complete problem, clique problem is NP complete, and vertex cover is NP complete by reducing the well known formula satisfiability problem to these problems. This is a reference. Thank you very much. We will meet in the next module, where we will talk about how to tackle the NP complete problems. Thank you.